today we're going to watch some children as they work on exercises in addition and subtraction. You know, when we ask children to find the sum of two numbers, let's say 17 and 15, the sum could be expressed this way. 17 plus 15. But what we really expect children to do is to express this number in simpler form. We are asking them to compute the sum. That is, to find what we call the standard name for 17 plus 15. Let's look at a few of the many ways of computing a sum. Each of these ways for finding the standard name for 17 plus 15 is called an algorithm. In arithmetic, an algorithm is a step-by-step procedure for renaming a number. These are different addition algorithms. This particular procedure could be used early in the grades in connection with joining sets to emphasize the idea of grouping by tens. Expanded notation is helpful for this purpose. Here we can see there's the adding of ones and then tens separately. Notice that in this algorithm, use is made of the associative property of addition. After children have an understanding of adding ones and tens separately, they might then be introduced to a somewhat simpler algorithm. Here, 17 and 15 are written in abbreviated form, the standard form. But there's still an emphasis on adding ones and tens separately. 7 plus 5, 12. 10 plus 10, 20. The ones and tens are added again to get 32. After children have had experience in working with algorithms that help them see how basic principles are applied, they are ready for the development of a more efficient algorithm. If this traditional algorithm is introduced too quickly, however, children may learn what to do, but they may not fully understand just what they are doing. For example, a child may say, 7 plus 5, 12, write 2, carry 1. But he might not know what he really means by carry 1. He should know that he is really cutting down on some of the notation that's used for this algorithm. These steps are combined mentally without any writing, and only the result needs to be recorded. We can also use different algorithms to develop an understanding of subtraction computation. Here, for example, is an algorithm using expanded notation where 42 is expressed as 30 plus 12. Now let's look at another procedure for computing that is a bit different. We want to find the difference of 42 and 28. Recall that if a sum and one of a pair of its addends are given, the missing addend is the sum minus the given addend. In this algorithm, we will make use of a principle sometimes referred to as equal addition. That is, the same number can be added to the sum and the given addend without affecting the missing addend. We'll use sets to give an illustration of this principle. Here are two sets. This set has 2 more units than this set. Now we'll enlarge both of these sets with the same number of units. The difference is still 2. Now here, for easier computation, we're going to add 10 to each of these numbers. Here we'll add 10 to the 2 ones and think 12 ones. But here, we'll add 10 to the two tens, and we'll think 3 tens. Now we subtract. What number plus 8 is 12? 4. Or to put it another way, 12 minus 8 is 4. And then 1 10 plus 3 tens, 4 tens. Later, we'll watch a child using this algorithm. Now, these are but 2 of many possible algorithms for subtraction. Now we're ready to work with some children. First, we're going to visit a second grade class, and we'll watch a child as she uses sets of objects to help her to understand the use of expanded notation in an addition algorithm.
1, 2, 3, 4, 5.
What are you working on? You working on that problem?
Yeah.
And you're using sticks to help you?
Yeah.
All right, show me what you do next.
Well, first you put the ones together right here, and then the tens.
I see. Do you know how many ones there are now?
12.
Oh, and then what do you do?
Well, take 10 of them and put them together.
And where do you put it?
With the other 10.
I see. And how many do you have altogether now?
30. I mean, what do you mean? 1,
Well, you have 30 here, and how many here?
2.
And altogether?
32.
I see. Could you work this out? Can you show me at the board how you work this out if you don't use the sticks? All right?
Okay.
What are you going to do?
Well, we have 17 plus 5.
17. What's that?
That means 10 plus 7.
And how about
Yeah.
15?
10 plus 5.
And now what do you do?
Add the ones
All right.
together. This is 12.
Can you separate that somehow
Oh.
to show me that's separate? I see. All right.
And then add the tens together, and that's 20.
Let's see. You have 20 plus 12. What is the 12 really?
10 plus 2.
Tell you what. Well, right here, 20 plus 12, and that's the same as 20 plus 10 plus 2, and the 10 plus 2 are together, so we'll show that this way. Now, the 10 and 2 are together. What are you going to do next?
Put the tens with the other tens.
All right. Shall we show it here? We'll show that 20 and the 10 go together. How can we show that they go together?
Just write 30.
We could. And to keep them together, could we make some sort of mark there?
Oh.
That shows that they are kept together. And then we can add the 2. Now, 20 plus 10 is a name for what number?
30.
I see. Want to write it here? 30.
Oops.
All right. Plus 2. And you want to write what you get up here? $17 plus 15 equals
32.
Expanded notation serves to clarify the part that decimal numeration plays in an algorithm. Note also how it helps children become aware of the associative property of addition. Now let's look at an algorithm that brings children closer to the familiar abbreviated computation procedure. In this addition algorithm, the sum of the ones and the sum of the tens are both indicated. Then these two sums are added to get the result. There is no regrouping or carrying here. The next stage eliminates some of this notation. Let's see. Did you use a long way or a short way for this one?
I used the short way.
Explain to me what you did.
Well, 8 plus 5 equals 13, so I put the 3 down and I carried the 1.
Carried 1?
110.
I see.
And 110 plus 2 tens equals 3 tens, plus 3 tens equals 6 tens, so my total would be 63.
That is a short way, isn't it? When we teach for understanding, children are likely to be more flexible in applying what they have learned. Let's see how an understanding of the properties of addition can enable a child to figure out his own way of computing. I understand you have a special way of adding sometimes. I wonder if you could explain how you do this example.
Well, I do it especially by grouping tens. And so I go 8 plus 2, that would be 110, and 6 and 4, that would be another. And 10 and 10, of course, is 20. Then I add the 2 to this 3, that would be 5. Plus another 5 is 10, plus 4 and 4, which is 8, of course, and that would be 18, or 18 tens.
I see. I wonder if you could tell me how you know you could skip around like that and still get the correct answer. For example, I notice you went from 8 to 2 and you skipped over the 6. Ordinarily, people might start with 8 and then add the 6 and then the 2, like this, 8 plus 6, and then add 2. How come you added the 2 to the 8? How do you know you can do that?
Well, because of two properties of addition, the commutative and associative. Now, the associative, which I use first, is without changing the order of the numbers, but changing the parentheses, like this. And that would be. And next you use the commutative property, which means you do change the order of the add-ins. And that would be.
I see, you're changing the order of these add-ins.
Yes. And again, we're going to use the associative property. And
you didn't change the order, you just changed the way that you group the add-ins.
yes.
I see. Now you have the 8 and the 2 together. So with this, with the associative and commutative properties, what does that allow you to do in addition?
Well, it allows you to change the order of the numbers and still have the same sum.
You change the order any way you like?
Yes.
All right, so that's your special way. Thank you. We have suggested several stages that might be gone through in developing efficient procedures for computing sums, using objects, expanded notation, and more abbreviated algorithms. Children can work through the same general stages in developing efficient algorithms for computing differences. Let's work with a child who has already gone through the stage of using objects to help with subtraction computation. What kind of problem is this?
Subtraction
And how are you going to do it?
with expanded notation.
I see. I see you've expanded the 42. How about the 28? How do you do that? Now what do you do?
I'm going to add in the ones before the 10.
You're going to add?
Subtract the 1.
Oh, this is a subtraction problem.
Yes.
And you're going to subtract the 1s. Can you do that?
No.
Why?
You can't take 8 from 2.
Well, what are you going to do? Let's see what you can do here. You have 40 plus 2. What can you do?
I could take 10 from the 40.
I see. You can think of the 40 as
30 plus 2.
30 plus what?
10.
Oh, I'll tell you what. Let's write it over here, shall we? We'll write 30 plus 10 for 40, and we'll show that they go together. And then you still have plus 2. Now, what are you going to do with the 10?
Add it with the 2.
I see. So we'll have 30, and then we're going to show that the 10 goes with the 2. How would you show that?
Put parentheses around the 10 and 2.
Oh, that would show they go together. Now, 10 plus 2 is a name for what number?
12.
So now we have 30 plus 12. Now we change from 40 plus 2 to 30 plus 12. Still the same number.
Yes.
Now, will that help you subtract? Let's see how. We have our 40 plus 2. Let's change it to 30, and we'll change this to 12. Now what do you do?
Then you subtract 12 minus 8 is 4.
All right. And then what do you do?
30 minus 20 is 10.
Let's write that. Then what? I see. And what's the answer?
14.
Bruce, I understand you started to do subtracting a shorter way.
Yes.
Let's try it out. I'm going to see how you do it. All right? I'll write the example over again. We have 42 minus 28. Show me how you do it the short way.
Well, you can't take 8 from 2.
That would be a neat trick, wouldn't it?
Yes.
Yeah.
So you take a 10 away from the 4 tens, so the 2 becomes 12.
Then what?
So 12 minus 8 is 4. And 3 tens minus 2 tens is 1 10.
I see. You remember you only had 3 tens left there, right?
Yes.
Tell me, Bruce, which way do you like better, this way or the expanded notation?
This way.
Why?
It's much shorter.
This is one of several short algorithms for subtraction. I saw a 6th grader using an algorithm that's taught in some of the schools in Europe. Let's have him show how he works a subtraction example. Craig, may I ask you something here?
Sure.
I understand that you have a different way of subtracting from the way that most of the children use. I wonder if you would explain how you work your subtraction example. Let's try this one.
Well, you go 7 plus what equals 5, and you can't do it, so you add a 10. That makes it 15. 7 plus 8 equals 15. You add a 10 here, so you add a 10 here.
Wait a minute, you added a 10 here,
Yes.
so you added 10 to this number here.
Yes.
I see, all right.
1 plus 4 is 5. 5 plus 4 equals 9.
For what?
4 tens
I see.
plus.
Mm-hmm.
And 2 plus 4 equals 6.
How do you know that if you add a 10 to this number and a 10 to this number, you're still going to get the correct answer?
Oh, well, you can add any number to the sum and the add-in. As long as it's the same number to both, the difference will stay the same.
I see. Thank you. Today we have seen children use different algorithms for computing sums and for computing differences. An algorithm, you remember, is a step-by-step procedure for renaming a number. As such, it's possible to learn an algorithm by merely memorizing certain facts and certain rules. Children can have a much more valuable learning experience, however, if they understand an algorithm. That is, if they can apply basic mathematical principles to justify each step in the algorithm. Bye.